In Lesson 5.3, Inverse Functions, we're going to take a step back to Algebra 2 and re-examine what it means for a function to have an inverse. Some functions have inverse that themselves are functions, and those are what we refer to as inverse functions. We're going to spend this lesson investigating those inverse functions, whether they exist, how to find them, and most importantly for calculus, how to find derivatives of those inverse functions at certain places on the inverse functions graph. So it's a lot of stuff we're going to cover, but let us begin by re-examining the very notion of an inverse. So let's see how much you remember about inverse functions from back in Algebra 2. Given a function, f of x let's call it, all we need to do is put in an x value, and what we'll get out is a y value. Simple enough, we've been dealing with functions for a very, very long time. But in an inverse function, what we're going to do is stick that y in and come out with an x. In other words, we're essentially doing f of y equals x in this case. Now you can see that these are very closely related. In a function, we give an input and we get an output. In its inverse, we can give it that same output and we should get the input that we originally put in. It's essentially just a role reversal of the x's and y's. Now we need to look at how to do an inverse function both graphically and analytically. So let's look at it graphically first. Over here you see that I've drawn you a simple coordinate plane with the line y equals x dashed going through it. Since all a function inverse does is reverse the x's and y's, the graph of it is simply going to be a reflection over that dashed line right there. Let me give you a quick example. Here is some random graph. It's a graph that we'll be looking a lot at in coming lessons. But if we look at that graph, I want you to imagine for yourself what this graph would look like if it were reflected over the line y equals x. Would the reflection of this graph still be a function? Well, let me go ahead and show you the case, and there it is. So you see the original graph is still there, but this new graph is the reflection, or rather the inverse of the original function. And as you can see, it does pass the vertical line test. So both the function and its inverse are both functions. How can we deduce this graphically without having to go ahead and reflect it every time? It's actually very easy. If the original function passes what we call the horizontal line test, and this is very, very similar to the vertical line test that we use to determine if an equation is a function back in Algebra 1, Algebra 2, whenever it was, we'd always check this vertical line test. Well, what we're going to do now is check that same function, but with a horizontal line test. If the function passes the horizontal line test, then its inverse will also be a function. And you can think of that yourself because every horizontal line will turn into a vertical line when it's inversed. So it makes a lot of sense. Well, fantastic. That's how we can do it graphically, but how can we look at this analytically? Well, that isn't too difficult either. If we have the function and we know its inverse, then we should be able to feed the inverse through the original function, and they should essentially cancel themselves out, so that we're left with just x, which, when you think about it, represents that diagonal line that we have there in that graph. Furthermore, if we feed the original function through its inverse, what do you think should happen? Well, of course, again, if it is a function and its inverse, they should essentially cancel out their operations, and we end up with just x. So, that's how we can tell if a function has an inverse. If the function passes the horizontal line test, that's graphically, or if we can find the inverse, and when we compose them together, the result is just x. Then we can tell analytically that the function has an inverse function. So now that we know this, let's go ahead and take a look at a couple examples here. We're going to be given a function. We're going to find its inverse. That's never a difficult thing to do because all we have to do for an inverse is just switch the x's and y's. That's easy. Just switch the x's and y's. But is our result going to be a function itself? That's what we'll deduce in the next couple of examples. Is the inverse a function? Let's take a look. So in our first example, we have this function f of x equals the cube root of 1 minus x. Given this function, we need to find the inverse and then graph both of them. So let me go ahead and start by just graphing the original function. And so there you go. There you go. It looks just like we would expect. It's a standard cube root function, although it is kind of flipped upside down because it's 1 minus x. And it's moved 1 to the right because it's 1 minus x, but no big deal. There's the graph of it. If we want to go ahead and try to find the inverse of this graph, well, let's go ahead and turn this f of x thing into a y. After all, that's what f of x really represents, is just y. So there's our original function. If we now go ahead and switch the x's and y's, let's see what's going to happen here. The y will turn into an x, of course, and we'll have the cube root of 1 minus y. Alright, so that's our first step, just switching the x and y's. What we really need to do now, because it does want the inverse in function notation, we need to get the y by itself. We'll begin by cubing both sides of this equation. That'll give us x cubed is 1 minus y, and it's only a short jump from there to figure out that y must be 1 minus x cubed. Or, if you like, put a different way, the inverse of x equals 1 minus x cubed, if that's how you prefer it. So, that being the case, go back, look at the graph of our original function, f of x, and imagine in your head, what is the inverse going to look like? Well, I'm going to give you just a second more to look at it, because there you go. There is the inverse. Notice that everywhere that the original function hits that line y equals x, that point stays the same under the inversion. Which makes a lot of sense, because if we're switching x and y are themselves the same. So it should be the same, really. But everywhere that we were going up, we're now going to the right. So that's just a natural consequence of that reflection over the line y equals x. And there you go. These are inverse functions. Notice that the original function did pass the horizontal line test. And if you want to, go ahead and plug the original function into the inverse and see if you don't arrive back at x. It's a beautiful thing. So, with that under our belt, let's take a look at one more example, one that involves a trigonometric function. This one will be fun and exciting. So here we go. We're going to do one more of these inverse functions. You see that our original function given is sine of x, and we are given a domain restriction on this. And that is for a very, very important reason. Let me show you by showing you the graph right here. There it is. And with that domain restriction, notice that we do pass the horizontal line test. If we didn't put that restriction in place, would the entire domain of sine of x, would that pass the horizontal line test? Clearly it wouldn't, because it is periodic and would keep going like this. So therefore, the inverse of y equals sine of x would not itself be a function. Fortunately, with that domain restriction, hopefully we've resolved that. So, let's go ahead and see what our inverse would look like. If we're given the equation y equals sine of x, and of course what we want to do is go ahead and swap the y and x, then what we would end up with would be x equals sine of y. And how are we going to solve this for y? Well, the way we get rid of sine, of course, is we just do the arc sine. Or if you prefer, sine to the negative 1 power, which is the way I'm going to write it here, without any loss of generality. We'll have arc sine of x equals y. And therefore, the inverse function of x is going to be, here I'll write it, as arc sine x. Alright, so what does y equals arc sine x actually look like? Well, let me go ahead and superimpose it over our sine of x, and there it is. Notice that it has a range restriction, because arc sine of x is actually going to be periodic as it goes up and as it comes down. So we had to put a range restriction on it, similar to the way we put a domain restriction on the original. Can you figure out what that range restriction is? How low and how high do the y's go here? Well, hopefully you can figure that out for yourself. But of course, it's going to go no higher than positive 1 and no lower than negative 1. And those are the exact answers I would get if I plug the domain restrictions into our original function. So there you go. Well, with that, let's go ahead and do a calculus-based problem now. Hopefully you'll enjoy example C. Here it comes. So far, we've seen how to tell if a function has an inverse function by means of graphing. Of course, when graphing, again, all it needs to do is pass the horizontal line test, and then we know that its inverse will be a function as well. So here's another cool little way we can tell without having to graph. What we can do is determine if a function is strictly monotonic. That is the function always increasing or always decreasing over its entire domain? Of course, if a function goes up and then begins to come down again, it's going to fail the horizontal line test. Inversely, if it goes down and then comes up, it'll fail the horizontal line test. So, we can conclude that if a function is always increasing or always decreasing, then its inverse will be a function as well. And again, always increasing, always decreasing, we call that monotonic. In other words, always going in one direction, mono. So, in example C, we're given this function here, and we're told to determine if it is strictly monotonic by using its derivative. So, of course, the first thing we're going to have to do here is go ahead and differentiate this thing. If we do this, of course, we're going to need the product rule. If I do the derivative of the first part first, what I'm going to end up with is 5 times the square root of quantity x minus 1. Now, because of the product rule, let me go ahead and differentiate the second part of this function, the x minus 1 part, or rather the square root of x minus 1 part. And if we do that, I'm going to do a little shortcut here, but you, of course, can do it by hand, and find out that the derivative of the second part would be 5x over 2 times the quantity x minus 1. Now, that's a bit of a mess. Maybe we can clean this up a little bit. It'll be a lot easier if it's all in one term. So what I'm going to do is multiply this first part here, which is 5 times the square root of x minus 1 over 1. I'm going to multiply that by this denominator right here. And if I do that correctly, what I should end up with, let's see here, I have 5 square root of x minus 1 multiplied by 2 square root of x minus 1. And that, of course, will be over 2 square root of x minus 1. And then, of course, I have this other part hanging out, the 5x over 2 square root of x minus 1. So if I go ahead and clean this up a little bit, I'm going to leave all the algebra to you. But what we should end up with, if done correctly, is 15x minus 10 divided by 2 times the square root of the quantity x minus 1. Now, this is the derivative. So if we go ahead and set the derivative equal to 0, what we're going to find is that we have a critical number at x equals, what is this? Let's see. X equals 2/3, or 10/15 if you like. Well, take a look at this. X equals 2/3 isn't even in the domain of the original function. Take a look at the original function. The domain itself, well, is going to be x is greater than or equal to 1, and 2/3 is not in that domain. So, if we take the interval from 1 to infinity, what can we determine about its derivative? Well, take any test value you like and plug it into this interval. Of course, 1's not going to work, but if we make it an open interval, not including 1, again, choose any test value, plug it into the first derivative, and what you'll find is a positive value. The first derivative is always positive over the entire domain of this function. Therefore, it is strictly monotonic. And as a result of that, its inverse would be a function as well. At this point, I'm going to encourage you, go ahead and graph the original function yourself in your calculator, and you'll see that it is always increasing. Furthermore, in your head, if you go ahead and look at the inverse of it in your calculator, you'll see that the inverse is a function as well. So, we're going to move on to example D, but before we do, let's go ahead and look at the derivative of an inverse function. Of course, we know how to find the derivative of the original function, And that being the case, we should be able to find the derivative of its inverse as well. Let me show you how. When concerning the derivative of an inverse function, it's important to note that the derivative may not always exist of the inverse function, even if the original function passed the horizontal line test. As an example, take a look at the graph I have drawn here. The blue represents the original function, while the red represents its inverse. Now, clearly the blue, the original function, does pass the horizontal line test, but does that mean that its inverse is always differentiable? And you can see, you can see clearly that that's not the case. In fact, at the point 0, comma 1, our original function has a derivative of 0. So the question now is, what happens at the inverse point on the inverse graph? Well, the inverse point would be 1, comma 0. And notice that there is no derivative at the point 1, comma 0. If there were a derivative, it would be a vertical line, which of course is undefined. So, the way we can formalize this is by saying that the inverse function is not differentiable if the original function has a derivative of 0. Once again, if the original function has a derivative of 0, which is what happened right here, then its inverse will not have a derivative at its inverse point. So that's very important to note. Now, what about all the other points? What I've done is I've drawn a black point here on the original graph, and I've drawn the inverse point on the inverse graph. What I want you to do is take a look at the derivative, or the slope of a tangent line at that point, and then take a look at the derivative of the point on the inverse graph. What do you notice about the slopes of these two lines here? Hopefully you can look at them and tell that they are in fact reciprocals of each other. This has a very, very steep derivative here, and this has a very shallow derivative here. And so the way that we can formalize that, and this is a little bit of a process, but the derivative of the inverse function is simply the reciprocal, and the way we say reciprocal is 1 over. It's going to be the reciprocal of the derivative of the function at its inverse point. And the inverse point I'll denote as the inverse of x. So this is a very, very important formula, especially when it comes to the AP exam. They're going to find ways to twist this around to make sure that you understand. But all we have to do is find the derivative at the point of the original function, and then we need to find the point that corresponds to that on the inverse function, and just realize that its derivative will be the reciprocal. It sounds a little bit confusing, but perhaps example C will help us sort all this out, or rather example D. So either way, let's go ahead and take a look at example D right now. In example D, I'm given an original function, which I've graphed here in blue for you. I'll call this f of x. And what we need to do is we need to find the derivative of the inverse of this function at the x value negative 11. So I've gone ahead and graphed the inverse function here in red. And the point that the question is referring to is the point where the inverse function is at negative 11. So you can see that's the point right here. And so what we want to do is find the derivative, or the slope of this tangent line. Now, given the original function, and seeing as how it involves x to the fifth and x cubed and all this, I don't really want to find the inverse function, although it does exist, certainly. It's graphed right here. If I could find the inverse function, I could differentiate it, plug in negative 11, and be done with this question. But that would be entirely too difficult for the scope of this class. So what we're going to do instead is find the inverse point on the original graph that corresponds to this point here. From there, we'll differentiate our original function and find the derivative at that point, and then we'll just do the reciprocal and have what we're looking for. So, of course, the first step here is to just go through and find what is the inverse point when we're dealing with the inverse of f at negative 11. And the way we do that is not entirely too difficult. We're just going to use our original function, and instead of this being x, because we're talking about the inverse, this is actually going to equal y. So the way this is going to look is negative 11 equals 1/27th multiplied by x to the fifth plus 2x cubed. Again, there's no calculus here. I'm just trying to flip the x's and y's and see what happens. So if we go ahead and solve this out, which I'm not going to do, but I certainly welcome you to do, it's difficult and might involve some guess and check and some graphing and all that good stuff. But what we should find is that x actually equals negative 3 when its inverse is negative 11. What that means is that at the point negative 3 comma negative 11, that is going to be the point on our original function that corresponds to the point that we're interested in our inverse function. See, what we could say is that this is actually the point negative 11 comma negative 3. And so in our original function, this is actually going to be the point negative 3 comma negative 11. And now what we want to do is find the derivative of the original function at that point. So that will be our second step, is to simply find the derivative of our original function. And of course, that shouldn't be too difficult. Since we've done derivatives a number of times, what we're going to end up with is that the derivative of our original function, well, let's see, that's simply going to be 1/27th multiplied by 5x to the fourth plus 6x squared. How did I do that? Well, I just did the derivative. No big deal. So now that I know that, let's go ahead and find what our derivative is at the point x equals negative 3. That shouldn't be too hard either. That's just a matter of sticking in negative 3 to our derivative. And if we do that, plug negative 3 in here and work it all out, what we should get is 17. In other words, the slope of this tangent line to the graph right here, the slope of this line is in fact 17. And now that we know that, we have one last step, and that's simply going to be to find the derivative of the inverse. So the inverse derivative at negative 11. And how are we going to do that? Well, not a big deal. Remember what we said. If the slope of this line is 17, then the slope of this line right here must just be the reciprocal, 1/17th. So, can that really be the case? Is it that easy? This has a very, very steep but positive slope. And this one, the inverse, has a very, very shallow but still positive slope. So that's how we do this thing. If you just follow these 4 steps, that will find you the derivative of the inverse every time that it actually exists. Be careful about that. And with that, let's go ahead and look at one last example for lesson 5.3. This is actually an example that's quite a bit easier than example D. So hopefully we have a good time with example E. In our final example, we're going to do something that's not entirely too difficult. We're simply going to try to find the derivative of this equation at this point 0, 4. Now, of course, to differentiate this equation, we're going to want to do this with respect to x, because you see we have dx on the bottom. So let me go ahead and write this problem as differentiating with respect to x. The equation x equals to natural log of y minus 3. Now, if we differentiate the left side of this equation, of course we'll get dx over dx, which is essentially just 1. But if we differentiate the right side of this equation, we've learned how to differentiate natural logs, and so what we're going to end up with here is simply 2 over y minus 3. But because we differentiated a y part, we're going to have dy dx here. Now, let's go ahead and do one last step so that we can have dy dx all by itself. All we need to do is divide by this fraction right here, and what we end up with is y minus 3 over 2 equals dy dx. Now, if we want to find the actual slope of the tangent line, or rather the derivative at the point 0, 4, what we need to do is evaluate the derivative at that point, 0, 4. Now, of course, there is no need for the 0 in this equation because there is no x. But if I plug 4 in for y right here, of course, what I will get is 1/2. Now, can that be right? Let me go ahead and show you the graph of this equation, x equals 2 natural log of y minus 3. There it is. There it is. And in fact, I've highlighted the point 0, 4 for you. what does it look like the derivative of this equation is? Now, of course, you might not guess 1/2, but given that we've already done the calculus and found that it is in fact 1/2, does it seem logical now that you see the graph? Hopefully you say absolutely yes, it does. And that is fun and exciting. So, we haven't covered a whole lot here in lesson 5.3, but what we have covered is extremely important because what's coming up is a couple very, very crucial inverse functions. Of course, in our last example, we dealt with the natural log, and you might know, you probably should know the inverse of natural log, but even if you don't, we'll be getting to that in the coming lessons. So that's why inverses are so important, so that we can understand natural log and its inverse, whatever that is. Of course, we talked about inverse functions in this lesson. We talked about what they mean. Essentially, we reversed the x's and y's, or graphically, we reflected them over the line y equals x. We know that a function will have an inverse function if the original function passes the horizontal line test, if it's on a graph. Of course, if the function is not on a graph, or we're not able to graph it for some reason, we can always check the monotonicity of that equation. That is it always increasing or is it always decreasing? If the answer is yes, then its inverse will be a function. And from there, we went ahead and looked at a couple examples where we actually found the inverse function to a given function. Essentially, again, it just involved reversing the x and y's and then solving for y. Now, it got a little more complicated as we went on. Starting with example D, we wanted to actually find the derivative of the inverse function at a certain point. So the first step to that process was to actually find the inverse point. A lot of times they'll give us the y, well, we need to find the x. Or they'll give us the x, we need to find the y. And that's so that we can switch them between the function and its inverse. After we found the inverse point, we went ahead and found the derivative of the inverse function at that point. Sometimes it's a process, sometimes it's real easy. On the AP test, a lot of times they'll give you a table, and you can just find the values you need and plug them in from there. Of course, once we found the derivative of the inverse function, if we wanted the derivative of the original function, or rather I reversed that, we found the derivative of the original. If we want the derivative of the inverse, it was just a matter of doing the reciprocal. If the original function has a slope of a over b, then the inverse function will have a derivative of b over a. It's simply the reciprocal, no big deal. So we didn't cover a whole lot, but what we did cover was extremely important and maybe a tad bit confusing. Certainly a little bit of practice will help you out. And in that vein, I certainly wish you good luck on this assignment.